Hello and welcome to this lecture. This and the next lecture we will see a couple of applications of projections and this distance minimization, which is very popular in engineering sub areas, and they've sort of taken a life of their own. There's the terminology associated with those ideas, and it's a pretty big area by itself. But at the root of it, at the base of it is simple projections onto an orthonormal basis, using an orthonormal basis onto a subspace. Okay, so I want to show both those examples and just bring out how linear algebra connects all of those together. Okay, so the first one is revolves around solving linear equations, least square solutions, specific, slightly variant, different from actually solving the equation. When you cannot solve, this is sort of the best you can do, the least square solutions, and how there is this idea of linear regression, which is very popular in machine learning today, and we'll talk about how that has roots on the least square solutions idea. Okay, so let's get started. Okay, quick recap. We've been talking about operators of late, and particular operators in inner product spaces. And when you have an inner product and a norm, there is this notion of orthogonality, and subspaces have orthonormal basis, and you can project any vector onto that subspace using the orthonormal basis, and you get the closest vector in the subspace. And so that anytime you solve an optimization like that in an elegant way, it has a lot of applications, right? So and then there are applications that come out of it, and let's see one of those primary applications, which is this notion of regression or least square solutions to a linear equation. Okay, so let's remind ourselves what linear equations are. You have so we'll predominantly stick with real valued real field vector spaces over real field in the applications, but many of the ideas can be extended quite easily. But let's begin with linear equations. A matrix is given to you, m cross n, and a vector m cross 1 vector column vector is given to you, and you have to find an x such that ax equals b. So this is the standard linear equation, and you know that there is solution if b is in the range of a. Range is the column space of a. Ax is simply an element in the range, so if b is not in the range, there is no chance that you'll have a solution. Solution exists only if b is in the range of a. Okay, so you notice one interesting observation, particularly when you have inner products and norms and all that. When the solution exists, the norm of ax minus b is equal to 0, right? It's exactly equal to 0. So when maybe you can find if there are infinitely many solutions, there may be many x's, but still ax is always b, right? So ax equals b, and ax minus b has norm 0. Okay, so in a way, when solution exists, the solution to ax equals b is actually the minimizer for the norm, right? So I mean, it's just when you have a solution, it all seems very redundant to think of it this way, but you can think of the solution in that fashion. Okay, so what is the solution to ax equals b? It's that x which minimizes norm ax minus b. Okay, when solution exists, of course, norm is non-negative, so norm goes to 0, right? So that's the least possible value it can take. So that seems to fit. So the idea is when there is no solution, what do you do? Okay, when b is not in the range of a, you can extend this minimization definition and get what's popularly called the least square solution to linear equations. Okay, so given a linear equation ax equals b, the least square solution is argument of the minimization of ax minus b over x. Okay, that x which minimizes norm ax minus b is your least square solution. Okay, so now the advantage of this is you don't have to bother whether b is in the range of a or not. Okay, if b is in the range of a, yeah, well and good, I will give you the best solution for the minimizer. If b is not in the range of a, I can still get something with the least square solution, right? So I have hope of getting something. Okay, so that's the nice thing about this least square solution. It not only gives you linear equations, so given that you have an inner product also in the space, it uses that to find the closest vector in the column space of A. Okay, so that's what. So your B is not in the column space, so you can't find an exact x. So you find an x which takes you closest to the B, right? So that sort of makes sense. So that's least square solution. Okay, what's the properties? Very quick properties to see. If b is in the range of a, least square solution coincides with the usual solution. That's easy to see. If b is not in the range of a, the solution to this problem is well defined. Okay, why is that? Because it's very easily connected to orthogonal projection. Okay. So, you might say, is the minimization over x norm ax minus b squared, is that well defined? You may want to use some calculus etc. to prove it, but we can use this notion of projection and elegantly conclude that the solution will always exist. Okay. So, why is that? Supposing you have m cross n matrix, A and B is an m cross n vector, ax equals b, the equation is given to you. You can define a subspace U as the range of A, okay? And then clearly you see that Ax belongs to range of A, okay? And B is some vector. So, the argument of minimization over x norm Ax minus b squared is the same problem as finding the closest vector in the subspace U, okay? As you vary x, Ax goes over all possible vectors in the range of A. So, you can redefine that as argument of minimization over U of the norm U minus B. So, all you are doing is finding the vector closest to B in the subspace U, and we are in an inner product space. So, you know that is all well defined, and you will get the closest vector in the subspace as the least squares solution. Okay, so notice what is going on. So, when B is in the range of A, you may have many solutions for x. When B is not in the range of A, you simply look at the projection of B onto U and solve for Ax equals that projection. Okay, so that is the idea here. So, you take the projection operator onto U, you know how to do that, and then the least square solution to Ax equal to B is the same as solving Ax equals PUB. Okay, instead of solving for B, you solve for the closest point of B to the inside the subspace that you want. Okay, so, it is sort of natural extension, but we know that this has a solution, right. So, there is no problem with worrying about does it have a solution or not. This definitely has a solution. Okay, PUB is definitely in the range of A, right. It's a projection onto U. So, it's in U. So, you will have a solution. Okay, you may have even infinitely many solutions for this. Okay, so this notion of a least square solution is used in linear regression and other such applications inside machine learning and other areas. So, what I have done to explain that is created a Colab sheet where I have taken some data in the spirit of machine learning from the real world. In fact, given that we are in the IPL season currently, I have taken data from IPL first inning score. So, you can go to some cricket websites, they will give you this data, you might have to write some scripts to modify them, etc. But I have created this matrix A here, which is a 20 by 747 matrix. Okay. So, you start seeing these kind of applications, right. So, a lot of linear algebra that we study, orthogonal projection, least square solutions, have applications in the real world, and when you go there, the sizes of these matrices are big, and you need these kind of tools to deal with them. It's difficult to, you know, just write them down, right. 20 by 747, why would I write that? In fact, I looked at the data, there's been about 760 odd IPL matches so far. Some of them have no result. I didn't take the no result matches. I don't know why. I just wasn't sure about it. So, I dropped all of those. I only took the matches which had a result, and that's 747 so far. And what is this 20? What is this 20 by 747? I'm going to take the number of runs scored in each over. Okay. So each column of A is one match. Okay. And the ith entry in the column is the number of runs scored in that over. Okay, there are 20 overs in an IPL match in the first innings. So, you look at the ith entry in a particular column, that would be the number of runs scored in the ith over. Okay. So, this file a.npy is a numpy saved file. I have given a link for you in there. You can go download that file and put it in your local disk or some Google Drive or something and access it from your own version of Colab. So, that will, and you might have to change the link there. So, that will give you the data. Okay. So, once you have this matrix A with you, you have all the data, right. And now you can start thinking of setting up some linear regression type problem. And I am going to show you one example. It actually may be a very bad example. I am just giving you one flavor. There are so many other problems where you can use the similar idea, but I am just picking up some very simple thing. Okay. So, what am I going to do? So, I have written a couple of commands here. I will come to this later, but let us look at this linear regression setup as I have explained here in the text. Okay. So, I am going to first define A10, which is a 747 by 10 matrix. I am first transposing that. I had 20 by 747. I am making it 747 by 20. It's just a transpose. It's easier to deal with. row I of A10 is the run scored in first 10 overs of match I. Okay, so hopefully that's clear to you. So every row is a match now because I've transposed it. Every row is a match, and I'm keeping only the first 10 overs. Okay, so why am I keeping only the first 10 overs? I'll tell you. That's what I want to do. So that's what I've done in the command here, right? So A of colon 10 comma colon, and then I've transposed it. So I'm keeping only the first 10 overs. I'll tell you why this learning problem is involving something like that. And then I have a number here which is A15T. Okay, so I have a vector here of length 10. For every match, it is the run scored in each over of each of the first 10 overs. That's my vector. And then I also have A15T, which is the total score of at the end of 15 overs of the ith match. Okay, so this will be a 747 by 1 matrix, and that's what I've done here. A15T, I'm summing up to 15th row of the matrix A and then transposing. Okay, so this axis 0 tells me that you do the column sum. Okay, so this is A15T is the total score at the end of 15 overs. Okay, so maybe you can sort of smell where I'm going here. I have the run scored in the first 10 overs, and I'm also keeping the total score at the end of 15 overs. Okay, so now we think of linear model. So what is this linear model that I'm thinking of? I'm going to hypothesize that the total score yi at the end of 15 overs in match I, okay, is a linear function of the vector xi, which is, the run scored in each of the first 10 overs. Is that okay? So I take this number of runs scored in each of the first 10 overs, and then I want to project, or I want to guess or predict what will be the total score at the end of 15 overs. Okay, so I don't know what's going to happen in the next 5 overs, but still, can I, using this data, come up with some estimate for what will be the total score at the end of 15 overs? Okay, so I'm going to hypothesize that that will be a linear function. Okay, so why linear function? Because that's the easiest I can deal with. So let's start with a linear function. So once I hypothesize it's a linear function, I only need these coefficients, right? A1 to A10, and I will multiply xi by A transpose. Okay, A I'm thinking of as a row vector. So if I do A transpose, x is a row vector, A transpose is a column vector, I'm simply doing a linear combination to give yi. So my hypothesis is a linear model, right? So yi is a linear combination. I don't know what the A's are, okay? So in any machine learning problem, typically you try to find these A's, okay? I have to now use the data that I have, this 747 data that I've collected, and then I try to find the value of A, okay? So what is the idea? So we will solve the linear equation, okay? So this gives you equations, right? We will do that with about half of the data, okay? I don't want to use all the data. So this is very typical in machine learning. This is how you work. You take half the data, 747, maybe half is some 400 or something, okay? I'm just taking 400 of the data points, and I'm going to solve the equation that I get using the least square solution, because I know least square solution will always be there. I mean, I may not get exact solution for these linear equations, the model may not fit, but I can always do a least square solution. So I'll get some answer, okay? So how do I know if that answer is any good? I can test the solution on the remaining data, right? So I take half the data, I compute the A, and then keep that same A and actually compute the projected thing for the remaining things and see what my error is. Am I doing good on the remaining data? So this is a method that machine learning normally uses. You take all the data, split it into two, you compute the model parameters using what's called the training set, the first training data, and then use that and test it on the testing set, which is what you've kept away. You use that use that model, evaluate your prediction on that model, and then test it out. Okay, so that's what I've coded here. You can see what I've done. I've taken A train as the A10 of colon 400. So only the first 400 matches I'm keeping, and Y train is the actual output. So I'll take the actual output for the first 400. And then NumPy has this implementation called LSTSQ, which is least square solution. Okay, so if I give you A and Y train, it will give you the solution for A. Okay, well, it'll give you many more things. So I'm just keeping A0. A0 is the solution, and you can see the answer. And I think if you look at it, most of you probably are not going to be surprised that each of these coefficients are around 1.5, right? I mean, if, without any further looking very closely at the data, if you were to guess from 10 overs what will be the score in 15, you're going to multiply by 1.5, right? You take the total and then multiply by 1.5. So that's the machine learning algorithm is sort of learning that, but there are some coefficients which are a bit off. I mean, there's 1.7 in the last one, there's some 1.4 in the third one, 1.7 odd in the fourth one. I mean, sort of around 1.5, but little bit off here, there. I don't know. I mean, this is what this data is telling you. God knows what happened in the first 400 matches. You can think of so many other factors here we're ignoring when we find just this, but this is okay. So you got some coefficients. Now, how good is your prediction? You have to test, right? So you take your A test and then Y test, and then you find your prediction. What's your prediction? You do the multiplication of A test by A0, right? So that's your prediction. Your Y test is the actual score, and you compute your squared error. Okay, Y pred minus Y test square. The star 2 just squares and NP sums. And then you can take root mean square, right? So you can divide the error by 347, which is the total number of test data, and then take the square root. So the answer comes out to be something like 14. Okay, so this learning method, at least for the data that I've given you, seems to be off by 14 runs in the IPL thing. So you may want to test it with other type of things. I mean, of course, the least squares with any linear model, this will be the best. You can't beat it with a linear model, right? So if you, for instance, if you just multiply the total score after 10 overs by 1.5, that will definitely be poorer than this, right? So because it can't be, this is optimized with this kind of test data. Okay. Now, hopefully this showed you what's going on here, how these equations are formed, and why this linear regression sort of relies on least squares in a very interesting way. So this is the idea. Okay, so you have data that you collect, and then you want to project or predict something. You assume a linear model, and every data gives you one column, so to speak, or one row in your matrix. Then you keep building it up. When you have enough data for testing, enough data for training, on the training you find the coefficient, on the testing you test how well you've done. So this is pretty good. So for instance, I mean, people who know cricket very well will tell you I'm ignoring some very important things when I look at my X, right? So maybe I have to add one more data point to X, which could be maybe the number of wickets that have fallen up to the 10th over, isn't it? That could be a useful thing, I mean, so maybe that number has to be added to the X, that data if you can pick up, and then maybe then you will improve this model, right? So even with the linear model, with that added data, maybe this 14 can come down further, right? So this is the sort of thing that people do in machine learning, right? Okay, so they think of what else to do, how else to do. Maybe linear is not a good function. If it's linear is not a good function, you go out of the realm of linear algebra. So that's not a course for us, but here is an example of this. Okay, so this Colab workbook and all of this is shared with you. You can click on this. I've embedded here. This file is with you. You can play around with this and see what I mean for sure, and understand this. So this is very typical of how this kind of idea is used in practice in machine learning applications. So hopefully that was interesting. So let's move on and try to look at this notion of orthogonal complement and projection. Okay, so we've been studying orthogonal complement, and we know that they are connected, right? So it's quite easy to see. If you have a subspace and if you have a projection operator, and U becomes the projection of a vector V, then this U minus V actually belongs to the complement, right? So it's a very standard thing. So V minus what you projected onto is orthogonal to the entire subspace. Okay, so that's a very standard result in this projection. So now you notice this slight twist on this. Okay, U is the closest vector to V if and only if U minus V belongs to U pub. Okay, so this is also a statement. I didn't quite put it like this maybe when we studied out the projection properly, but you can see that this is true, right? Out of all the vectors that are closest to V, right, I mean, out of all the vectors in U, the vector that is closest to V is that one which will satisfy this. U minus V has to be in the orthogonal complement, not, okay, only then this will work out. It's the same orthogonality condition. So notice how this will subtly transform itself into something else. Okay, So now how do you do this testing? How do you find if u minus v is in u perp or not? It's not very hard, right? So you take any spanning set for u, I'm going to say spanning set, it could be a basis but maybe not, I mean I don't care, any spanning set for u, then u minus v is in u perp if and only if this inner product is 0, isn't it? So each of these spanning vectors inner product with u minus v has to be 0. If that is true, then clearly this is in the u perp. If this is in u perp, this will also be 0. So this is an if and only if. Okay. Notice where we are going here. You will see this, we are going into an interesting direction as far as orthogonal complement is concerned. We had one way of doing the orthogonal complement. I will give you another way of thinking about the orthogonal complement. In other words, this u, which was the orthogonal projection of v onto the subspace u, is also the unique solution to this set of equations. You take any spanning set for u, it is the unique solution to ui comma u being equal to ui comma v. This inner product being 0 for all of the vectors in the spanning set. Okay. So this is another way of doing the projection. Instead of doing the projection, you find the orthonormal basis and take the inner product and do that. That I think is quite an easy process. You can also do something like this, but this is also the same. It's not anything different, right? So you go to a equation of this form. Okay. So hopefully this was clear. It's just we are just using the orthogonality in a very interesting way with a spanning set for u. Okay, because we know that u minus v is in the complement. So you take a spanning set for u, then you get a set of equations, and these are linear. I mean this is all inner product, so it's all linear. So it's very nice to write down. Okay. So now when you want to solve linear regression, there is an equation that you can write using this the previous property that we studied. Okay, take a spanning set and do that. Okay. So you have a m cross n in the linear regression setting. You have a m cross n matrix A. I'm picking it as real for this purpose, but you can even extending to complex is also very easy. B could be a real vector. B is a real vector. I'm going to define u as the range of A. Okay, it's the range of A. This is the subspace u which we have been trying to project onto, right? So let's say AI is the ith column of A. So notice, why am I worried about the columns of A? I'm looking at range of A. So because this will give me a spanning set for you. Okay, what is the spanning set for you? A1 to An, the columns of A. Okay. So notice how I will move into this inner product thing. So the closest Ax to B, okay, the closest Ax to B, remember Ax is an element of U, right? Closest Ax to B satisfies Ax minus B is in U perp, right? This is a very simple little relationship that we have seen before. Or, okay, what did we see about how to check for Ax minus B belonging to U perp? Or the inner product of each of these columns of A with Ax minus B has to be 0. Okay, these are all equivalent conditions. We know that all this has solutions, right? Because projection exists. We know they can project. So all of these have solutions. There's no need to check anymore. So this inner product of AI with Ax minus B has to be equal to 0 for every I. This is the same condition as projecting and solving. Right? So there's no difference here. So in other words, you write this for every I, which means every column inner product with Ax minus B goes to 0. But how do I write every column? So I can simply write it as A transpose multiplying Ax minus B. Notice what happens if I do A transpose. If you want, I can write out what A transpose will be. A transpose will simply be A1 here, A2 here, so on till An here, isn't it? Right? Now I want to take inner product with Ax minus B. What is A1 inner product with Ax minus B? So now I can write Ax minus B here, right? This will be just a column vector. So this into this will give you every value being inner product, and that has to be 0 throughout. Okay. So that's the same condition here. A transpose into Ax minus B equals 0. You see, I keep writing 0 on this side. Remember, 0 is, you put as many zeros as you need on the column. Okay. So that's how you think about it. So this other thing, the same thing, now you just multiply it out, you get this very interesting looking equation. A transpose Ax equals A transpose B. Okay. And how do I know that this equation always has a solution? Of course it has to, right? It's the same as the orthogonal projection. Orthogonal projection exists, so definitely this equation will have solutions. Okay, so a nice looking equation which you can directly look at from E. So solution always exists. There are various ways to show that solution always exists, even if you don't like the inner product approach. We will do that later on for the equations like this. But when you have inner products and when you have projections, solution will always exist for this by the orthogonal projection that we are looking at. Okay. So this is another way of thinking of linear regression. You will see a lot of, so in fact, if you start with, so if you start with norm ax minus b squared and minimizing over x, and if you do calculus, what is calculus? You differentiate with respect to x, xi, and equate to 0, you will get this same equation. Okay. So that's another way in which people come to this A transpose A equals A transpose B. We came to it in using our orthogonal projection, but all of them are the same. Okay. So there can be very many ways to solve the problem, but at the end of the day they solve the same problem in one way or the other. Okay. So thank you very much for listening up to this point. We will look at another application in the next lecture, which is quite interesting in its own right, but it's very different from this application. Okay. See you then.